Hello again, Math 10Cs. In today's lesson, we're going to talk about a special type of relation that's referred to as a function. And just as a quick reminder in terms of what a relation is in math, you can even see the definition part of the way down the page here. In a relation, each element of the domain, the input, is related to an element or elements of the range, the output. So I can give an example of what a relation would look like. So let's pull up my pen here. Okay, so you could have, like, for example, y is equal to 3x plus 1. Your input would be x. Your output would be y. And then what it's saying is each element of the domain, the input, is related to an element or elements of the range. So for example, like let's say you plugged in like x equals 1 into this equation. Okay, x equals 1. Then you would have y is equal to 3 times 1 plus 1. Then you'd have y is equal to 4. So when it says here that each element of the domain, so one element of the domain would be x is equal to 1, and that relates to one element of the range, which is y is equal to 4. So when x is equal to 1, y is equal to 4, and that's a mathematical relation. Before we get into defining what a function is, we're going to go through this little exploration activity that kind of sets it up. To illustrate the concept of function, we will look at two relations described in words with a domain that has values of 1, 4, 9, 16, and a range with values 1, 2, 3, and 4. Now, the mapping diagram we're going to look at on the left-hand side is going to be in the format one number is a multiple of a different one. Okay, now this might seem kind of confusing in terms of what it's actually talking about here. So it basically means this. If you start off with the number 1, let's try to fill in the sentence here. So we'd say 1 is a multiple of, and which numbers is 1 a multiple of? Well, only 1. 4 is a multiple. You go up here. 4 is a multiple of 1, and 4 is also a multiple of 2. Therefore, we have two arrows that are coming out from this value in the domain. How about 9? 9 would be a multiple of 1. So we can draw an arrow up here. And 9 is also a multiple of 3. So you can draw an arrow there. How about 16? 16 is a multiple of 1. 16 is a multiple of 2. 16 is also a multiple of 4. And we're actually missing one other one here. 4 is also a multiple of 4. So I'll do a black line. So 4 is a multiple of 1, 4 is a multiple of 2, and 4 is also a multiple of 4. So that's a mapping diagram that shows how these values for the domain or the input are a multiple of the values of the range or the output that we have on the right-hand side here. Okay, now we also have this one that says one number is the square of another one. So 1 is the perfect square of 1. 4 would be the perfect square of 2. 9 would be the perfect square of 3. And then 16 would be the perfect square of 4. Just draw a comparison between the two mapping diagrams. This mapping diagram on the left-hand side is like quite a bit more complicated because you have all these overlapping lines. The mapping diagram on the right-hand side is pretty simple because for each value of your input, you only map to a single value of the output. On the diagram on the left-hand side, for example, like for the number 4, for this input value, it actually maps to 1, it maps to 2, and it maps to 4. So it actually maps to 3 numbers. And that's going to determine whether or not we can classify this special relation as a function or not. But we'll get into that in a bit here. Okay, B says write down as ordered pairs. Okay, so again, this is your input, this is your output. These are your x values, these are your y values. So if we follow the mapping diagram, when x is 1, y is 1. When x is 4, y is 1. When x is 4, y is also 2, so we can write down 4 comma 2. When x is 4, y is also 4. When x is 9, y is 1. When x is 9, y is also 3. When x is 16, y is 1. When x is 16, y is also 2. And when x is 16, y is also 4. Okay, so those are all the different ordered pairs that show how x is related to y from this mapping diagram. You can do the same thing for this mapping diagram on the right. When x is 1, y is 1. When x is, again, this is x and this is y. When x is 4, y is 2. When x is 9, y is 3. And when x is 16, y is 4. Now it wants me to plot these points on a grid. Okay, so we'll have, let's draw the grid lines, 1, 2, 3, 4. This is a really strange grid because it's not, there's not even spacing between the numbers, but that's okay right now. So let's plot these points. So we got 1 comma 1. Let's do it in red actually, so it can stand out a bit more. Okay, so here's 1 comma 1 at this point. You have 4 comma 1, which should be here. You have 4 comma 4, which should be all the way up at the top. You also have 4 comma 2, which should be located here. Okay, so we got 1 comma 1, 4 comma 1, 4 comma 2, 4 comma 4. We got 9 comma 1. And we have 9 comma 3. We have 16 comma 1. And we have 16 comma 2. And then we have 16 comma 4 up the top there. For the graph on this side, we have 1 comma 1, which would be located here. We have 4 comma 2, be located at this position. We have 9 comma 3, located there. And we have 16 comma 4, which would be up in the top right here. Okay, so we just used a mapping diagram to identify the ordered pairs in the mapping diagram, and then also to sketch a graph of what those ordered pairs would look like. Now we're going to the next page where we're going to define what a function is. Okay, it says a functional relation or a function is a special type of relation, and this is the key part of it. It says each element of the domain can be related only to exactly one element of the range. Okay, so each element of the domain is related to exactly one element of the range. If any element of the domain is related to more than one element of the range, then the relationship is not a function. Okay, so let's go back to the previous page and identify which of those two relations is a function and which of them is not. Okay, let's look at the one on the right-hand side. Okay, so let's look at this one. X is the square of y. Now, if this relationship is a function, what that means is that for every input value, it relates exactly to one output value. Okay, no problem here, because an input value of X relates to exactly a single output value of 1. An input value of 4 relates exactly to a single output value of 2. An input value of 9 relates exactly to a single output value of 3, and a single input value of 16 relates exactly to an output value of 4. Because of that, we would call this a function.
Could the owner of a silver Acura that is parked behind the building please call 0, the owner of a silver Acura?
Okay, so the relationship is called a function if you take a number in the domain, an input value, and it relates exactly to one output value. Now, if we go over to the other picture, we're going to see that this one is not a function. Okay, so let's check this. If X is 1, it actually does relate to a single output value, no problem. Okay, so if we were using just that point to identify if it's a function or not, it would pass the test. The problem is when you get to number 4, okay? If X is 4, if it's a function, it has to relate only to exactly one output. The problem here is that it relates to 1, it relates to 2, and it relates to 3 outputs, okay? So the instant that a single X value in the domain relates to more than one value in the range, then no longer is it going to be a function. And it would also fail for the 9 because 9 is related to, it maps to 1, and it also maps to 3. 16 also fails because it would map to 1, it would map to 2, and it would map to 4. If I want it to be a function for each domain value, input value, you can relate exactly to one output value. So this one is not a function for that reason. Back to the second page. Example 1, in the exploration on the previous page, one of the relations is a function and the other one is not. We already identified that. Explain how we can determine which relation is a function by looking at the following. Part A says, if we look at the arrow diagram, how do we know whether we're looking at a function or not? Well, I kind of already clarified that. So what I would say here is only one arrow can leave each element. When I say each element, I just mean each number in the each number in the domain. So only one arrow can leave each element in the domain. The instant that you have more than one arrow leaving a number in the domain, it's no longer a function. So again, if we go back here, the reason this guy's a function is because you only have one arrow coming out of each element or each number in the domain. This one's not a function because, for example, you take the number 4, you have 1, 2, 3 arrows coming out of that number. So it doesn't meet the criteria of this special thing called a function. Okay, how could you use the ordered pair to identify whether it is a relation, of whether the relation is a function? So the key thing right here is that if you look at the ordered pairs, the instant that you see more than, like, for example, let's pick this one. If I was just looking at the ordered pairs, the instant I see the input values repeat, like you have 4, 1, 4, 2, 4, 4, because what that means is that the number 4 would relate to, the x coordinate of 4 would relate to a y coordinate of 1. 4 would relate to a y coordinate of 2. 4 would relate to a y coordinate of 4. So because your x coordinate, which is your input value or your domain value, is mapping to more than a single value for the range, it's not a function. Okay, so let's summarize that. So I'm going to say each distinct x coordinate has only one y coordinate. If an x coordinate has an x value like 4 or 16, so say like you have an x value of 16, if it has more than one y coordinate attached to it, then it is not going to be a function. How about the graphs? What about the graphs can be used to determine this? Well, I'm actually going to jump ahead for a moment and just kind of just clarify the test we can use for a graph to determine whether or not it is a function or not. So I'm going to go over to the next page. We're going to look at this section called the vertical line test. Okay, the vertical line test is going to help us identify whether or not a relation is a function based on a graph. And then I'll explain why this test is true. So the vertical line test can be used on a graph or relation to determine whether the relation is a function or not. If every vertical line drawn on the domain of the relation intersects the graph exactly once, then the relation is a function. If any vertical line intersects the graph more than once, then it is not a function. Okay, so this is what this means. So let's say you had a graph that looked like, okay, here's my XY axis, and you have a graph that looks like this. Okay, it's like a curve shape to it. Now, the vertical line test basically means is if you put a vertical line through anywhere on the relation, if it only intersects the graph one time, then it's a function. So for example, let's say that I took a vertical line and I drew the vertical line just going straight up like this. It only hits the graph one time, intersects the graph one time at that location. So this one is a function. It doesn't matter where you draw the vertical line, no matter what you do, it'll only intersect the graph a single time, in which case it's a function. Now, let's take a different type of graph. So let's go to my XY plane and let's do a curve this time around that looks something like this. And if I do the vertical line test this time, so the vertical line test would be, if you draw a vertical line, okay, so let's do it right here. There would actually be two intersection points. There would be one at the top and there would be one at the bottom. So you have two of them. And if you have more than one intersection point of the vertical line, then it is not going to be a function. Okay, let's go back to the first page and explain why this is the case. Okay, so let's look at the graph here. Okay, so looking at this graph, which of these is a function and which of these is not? Well, you want to do the vertical line test. So if I do a vertical line, and let's do green color. Okay, if you did a vertical line at x equals 1, no problem, okay? It would only pass through a single point. But the issue here is that if you do a vertical line at, it's not a great vertical line. I want to get it so it actually hits these points. Where did my line go? Yeah, so here's the issue. If you draw a vertical line at x equals 4, it actually passes through multiple points. So that's a problem. And this is the reason why it's not a function, because the key thing is if you have a function, if you have a distinct x value, so my distinct x value here being x is equal to 4, you're only allowed to have one y value attached to it. The problem is that if x equals 4, you actually have 1, 2, 3 y values that are attached to that line. And in order for it to be a function, for every x value, you can only have one y value attached to it. So that's why the vertical line test would fail. Because if a vertical line passes through multiple points, it tells you that for a given value of x, you actually have more than one value of y, therefore it doesn't work. If you looked at this graph, it doesn't matter here where you actually draw a vertical line. Like you could do it through like this point. If you draw a vertical line straight up, it's always only ever going to pass through a single point. So therefore, this one would be a function, okay? Because it does pass the vertical line test. All right, let's go over to the second example. It says each of the following is a graph of a relation. So you have graph A, B, C, and D, and it wants me to complete this table by identifying true or false statements. Okay, so I'm going to grab a different pen color. Okay, so for each input value, there is only a single output value. So let me give you an example of that means. Like, let's say, for example, that if we looked at what the value of, if we looked at x equals 1, then what would the y value be? Okay, so what I'm actually going to do is I'm going to draw a vertical line through this to identify like whether or not this statement is true. So let's go back to my vertical line. Okay, so on the graph on graph A, if I were to draw a vertical line at x equals 1, okay, my vertical line would look like this. Well, it's a little bit off-centered, but let's try to get it so it actually goes directly on here. Okay, that's okay. Now, if you look at the relation, so for an input value of x equals 1, do you only have a single output value? Yes, because if you go across to the graph here, it would hit the y. It would have a y value that's equal to 1. So for graph A, that is a true statement. So we can put T for true. Okay, graph B. Again, we're going to do this all by drawing a vertical line at x equals 1. Okay, x equals 1. We'll do x equals 1 would be right here. Okay, so vertical line. Draw this one here. Program keeps making my lines a little bit off, which I'm not happy about. There we go. Okay, x equals 1, vertical line. X equals 1, vertical line. Okay, so for each input value, there's only one output. So let's do it for all these graphs here. Okay, this one, no problem, because when x is 1, y would be equal to 4. So that's true for graph B. Now for this one, this is a problem. Because if you look at this one, if you draw a vertical line at x equals 1, for x equals 1, you actually have two possible y values. You have a y value here, and you have one at the very top. So that's not true. Okay, for x equals 1, you'd actually have two output or two y values. So that'd be false. And the same thing for this graph. You actually would have two spots where it crosses this graph. Therefore, that would also be false. Now it says for each output value, there is only one input value. Okay, so it wants me to do the other way around here. So what that means is, let's say if y was equal to 1, then what would the value of x be? I'm going to draw a horizontal line to show this. Okay, so we'll do a bunch of horizontal lines at y is equal to 1, or passes through the y-axis at y equals 1. So let's go here, and I'll do it in a different color. Okay, let's do it in red this time. Okay, so y equals 1 would be here. Okay, y equals 1 would be at this location. Actually, y equals 1 is not going to be great, because let's do no, it's okay. It's just not going to be good for graph C. Okay, y equals 1 here. And whatever, for this one, let's just do y is equal to 5. Okay. Let's go back to my pen. Okay, so if y is equal to 1, do you only have one input value, x? No. This one right here, you'd actually have 2. You'd have two input values. You'd have one at x is equal to -1, and at 1 at x is equal to 1. So this would be false. And then for this graph, for your one output value, which is y equals 1, do you have a single input value? Yeah, you have one input value, and that'd be right here. So this would be true. For this one, okay, instead of doing y equals 1, for this one, we'll just do y is equal to 5. So for x, y is equal to 5, do you have a single input value? No, you have 2 of them. Okay, you have one here and you have one there, so that would be false. And then for this one, if y is equal to 1, do you have a single input value? Yeah, because it just crosses the graph right here. So this would be false. Now, this third bullet point wants me to identify, is the relation a function or not? Now, the key thing about a function is that it only has to pass the vertical line test, okay? Which means if it passes the vertical line test, then for each input, there's one output. The horizontal line means that for each output, there's only one input. Okay, so let's note the difference right here. If an input value only has one output, that doesn't necessarily mean that the output value only has one input. Okay, so really to identify what a function is, this is really the important thing at the end of the day, is just simply identify, does it pass the vertical line test or not? Okay, so if I look at graph A, if I draw a vertical line through any point of the graph, it would only ever hit the graph at one location. Therefore, that would be true. For the second graph, does it pass the vertical line test? Yes, because it doesn't matter where you draw that green vertical line, it would only pass through the graph a single time. So that would be true. Graph C, does it pass the vertical line test? No, because there's various locations where if you were to draw a vertical line, then it would pass through the graph more than one time. So that would be false. And for graph D, does it pass the vertical line test? No, because there's a lot of different locations where if you draw a vertical line through the graph, it would pass through it at more than one location. So that would be false. So really the key thing is you're trying to identify whether or not something is a function or not. You're just looking at this row, okay? You're identifying for each input value, is there only one output value? And if that's the case, it means that it would actually pass the vertical line test. This is not a criteria to define a function, okay? For one output value, there's only one input, okay? So that's not necessary to define a function. All right, so let's go all the way over to example number 3 now, and let's try to identify whether these are functions or not, based on like either the vertical line test or the rules that we identified in the previous page. Okay, so For A and B, we have coordinates. Okay, so let's go back to our rule for like what the coordinates are in terms of identifying a function. Oh, for graphs here, we should fill this in. How can we determine if it's a function or not? So I'll say if the graph passes the vertical line test, then it is a function. Okay, so in terms of the ordered pairs, so in order for it to be a function, for each distinct x coordinate, you're only allowed to have one y coordinate. So let's look at what we have here. Okay, so for a distinct value of x equals 5, we have y equals 8, so no problem so far. For a distinct value of x equals 6, we have y is equal to 7. Okay, so no problem. 6 maps to 7. If we have -5, that maps to -3. Okay, we have 2 would map to +3. Now here's where it fails. Okay, so the issue here is that you have 6 that's attached to 7, and then you have 6 is also attached to 8. So for each distinct y coordinate, you can only have, for each distinct x coordinate, you can only have one y coordinate. And since you do not here, this is where it's going to fail. So I'll say no, because x equals 6 has 2 y coordinates. How about this one? Okay, so when x is 3, y is 3, no problem. When x is 2, it maps to 3. Okay, so again, that's not an issue either. Okay, I know the y coordinate repeats twice, but the key thing is that for each distinct x coordinate, it has a y coordinate. Okay, it doesn't matter what that y coordinate is. So 3 maps to 3, 2 maps to 3, 4 would map to 5, and -3 would map to 2. So the reason this guy is a function is because, so I'll say yes, for every x coordinate, there's only one y coordinate. C, mapping diagrams. Let's go back to our rule for a mapping diagram. So if it's a function for a mapping diagram, it means only one arrow can leave each element in the domain. Okay, so let's go back here. So for A, so this is the domain, this is the range. There's only one arrow leave A. Yes. Okay, so good. Does only one arrow leave B? Yes. Does only one arrow leave C? Yes. So again, as long as only one arrow leaves every single element in the domain, even if they both go to the same y coordinate, it still is a function. Okay, only one arrow leaves each element. Okay, so let's clarify that. So I'll say yes, only one arrow leaves each element of the domain. Okay, D, so it's a graph. So the question right here is, do you pass the vertical line test or not? And right away you can see it doesn't, because I could draw a line that goes straight through here. So that fails. No. Fails the vertical line test. E describes the relation in a complete sentence, says the relation connecting the provinces and territories of Canada, their capital cities. So basically what it means is for each province or territory, is there a distinct capital city? Yes, okay. So that'll be a function. So yes, for each province or territory. There is only one capital city. F and G, we're going to do the vertical line test. So F is okay. It doesn't matter where you draw a vertical line. You could put it here. You could put a vertical line here. You could put a vertical line here. Put a vertical line right here. It doesn't matter where you draw it. If the graph only intersects the vertical line a single time, then it is going to be a function. So I'll say yes. Passes the vertical line test. G, you can clearly see that it does not pass the vertical line test. So I mean, I could just draw like a line that goes through here and actually have it hit at 1, 2, 3 points. So that would fail. Therefore, that is not a function. And let's go to the last page. Okay, here's where the notation starts to get a little bit funky, and that'll kind of continue into the start of the next lesson. It just takes a little while to get used to this. Okay, so a function as a mapping. A function from a set D, the domain, to a set R, the range, is a relation in which each element of D is related to exactly one element of R. Okay, we've already been talking about that. We said that that is what defines what a function is, okay? A function is a special relation where each distinct element in the domain can only relate to exactly one element of the range. If the function f maps an element x in the domain to an element y in the range, we can write down the following little notation. Okay, so what this means here is f is an abbreviation for function. Okay, and what does it mean to have a function? A function is when you have each element in the domain x relates to exactly one element in the range. So the way I would think about this, if you're trying to translate it, you can think of like f as here. So let's just kind of do just like one on top of the other. Okay, so f would be an abbreviation for a function. So what is a function? A function is where each x element relates. So that little arrow that's coming out of x, you can think of that as being relates. Each x element relates to one y element. Okay, so it says complete the following for the relation of is the square on the first page of the lesson. Okay, so that was the one where we had a mapping diagram. I'll just quickly sketch the mapping diagram so you don't have to go back here. Okay, so that's where we had a mapping diagram that looked like, okay, got this oval, we got this one. We had 1, 4, 9, and 16. We had 1, 2, 3, and we had 4. And if we drew our arrows, they all just went straight across. 1 is the perfect square of 1, 4 is a perfect square of 2, 9 is a perfect square of 3, 16 is a perfect square of 4. Okay, these are all my elements that represent the domain, so my x values. These are all my elements that represent the range, my y values. Okay, so it says complete the following for the is a square of the first lesson. Okay, so what this means right here is how does x relate to y? Well, if x is 1, then y is 1. How does x relate to y? If x is 4, if x is 4, then y is 2. If x is 9, how does that relate to y? Well, if x is 9, y is 3. And then the last one here is we got to fill in both of them. So if x is 16, then y is 4. So all the arrows telling you, it's telling you just how the x and the y value are specifically related to each other. Okay, let's look at this example. I think this is actually where the lesson ends off at. Unless I'm mistaken, but I'm pretty sure that's where it goes to. Good. Okay, consider the function. So again, f is just an abbreviation for function where x relates to, so again, the key thing here is like x relates to y. So what this is telling you here is that it's telling you the relation would actually be y is equal to 3x plus 1. So what it's saying is if you plug in a value of x, if you want the value of y, you then have to plug that value of x into this expression, 3x plus 1. Okay, and we're going to do it for a domain of -1, 0, 1, and 2. Okay, so let's go ahead and do this. So this is the value of x. So if x is equal to -1, what I do is I take x equals -1 and plug it into this equation. So that would then be y is equal to 3x plus 1, which would be 3 times -1 plus 1. And that would be equal to 3 times -1 is -1 plus 1 would be -2. So when x is -1, what's the value of y? -2. Okay, what if x is equal to 0? Well, just plug x equals 0 into the equation. So you plug x equals 0 and now we're going to replace x with 0. So it'll be y is equal to 3 times 0 plus 1. 3 times 0 is 0 plus 1 would just be 1. Therefore, when x is 0, y is 1. How about when x is positive 1? When x is positive 1, plug that into the equation for x. So then you'd have y is equal to 3 times 1 plus 1. 3 times 1 is 3 plus 1 would be y is equal to 4. Therefore, when x is equal to 1, y would be equal to 4. And then my final value in the domain, when x is equal to 2, we're going to plug that into the equation to calculate the value of y. So 3x plus 1, so that'd be 3 times 2 plus 1. 3 times 2 is 6, plus 1 would be 7. Therefore, when x is 2, we would have y is 7. Okay, so that just shows how each distinct x element relates to the y element. Okay, list the elements of the range of the function. Okay, so the domain's identified up here. So the range, we just have to write down what the different possible y values are. So we just write down range, r for range would be, okay, where are the possible y values? Write them in ascending order. So the smallest one is going to be -2. Then we have my y value of +1. Then we have a y value of 4. And then we have a y value of 7. Okay, so that's my range. Okay, C, show this as an arrow diagram. Okay, so let's do my two ovals here. Okay, first oval is going to be your x value. Second oval is going to be your y values. So what are my domain values? If we look up here, we have -1, we have 0, we have 1, and we have 2. What are my range values? You have -2, you have 1, you have 4, and you have 7. And then we use the arrows to map this or connect this. So when x is -1, y is -2. When x is 0, y is 1. When x is 1, y is 4. And when x is 2, y is going to be equal to 7. Okay, so that's my mapping diagram. And again, it shows it is a function because you only have one arrow coming out of every single x value in the diagram. Okay, write this as a set of ordered pairs. Okay, when x is -1, y is -2. When x is 0, I'm using the mapping diagram, y is 1. When x is 1, y is 4. And when x is 2, y is 7. And again, you can check that this one's a function looking at the order of pairs because for you shouldn't see any repeating x values. Okay, the instant you see repeating x values, it means that you're going to have more than one y value attached to a specific x coordinate, which no longer makes it a function. Okay, draw this on a Cartesian graph. Okay, let's just quickly scale this. So let's make the x-axis. It goes up to a maximum of 2. So we have -1, which would be here. And then we'd have -1, 0, 1, 2. That's as far as it goes, actually. And then the range goes from -2 to +7. So you'd have -2, -1, 0, and then 1, 2, 3, 4, 5, 6, 7. Let's plot these points. Okay, so -1, -2 would be 1 to the left, 2 down. So that'd be located right here. Then we have 0, +1. So that would be starting at the origin, just go straight up here. Then you have 1, 4. So go 1 to the right and then 4 all the way up like that. And then you have 2 to the right and then 7 up, which would be right here. And again, we know this is a function because it doesn't matter where you draw a vertical line, it would only pass through a single point. And again, that is the ultimately at the end of the day, probably the easiest way to identify whether something is a function or not is if you graph it and you do the vertical line test, the vertical line can only pass through the graph at a single point. That's the easiest way to visualize what a function is, where function is just a special relation. That's it for the end of this lesson. So you can practice this by completing on page 459 and do numbers 1 through 10 and do all of the parts. And I'll talk to you in the next lesson.